Okay, great. In the previous video, we introduced multiple linear regression, right? And we said in this video, we are going to see how do we estimate the coefficients for multiple linear regression. For simple linear regression, we saw how we estimated. But what about when we are regressing on many variables? How do we do that? So, just as in the case of simple linear regression, the true betas, they are not known, right? But what do? We try to estimate it. For beta naught, we estimate it with a beta hat naught. Then for beta 1, beta hat 1. All the way up to beta p with a hat as well. So these are going to be estimates. We try to estimate them because we do not know the true coefficients. We do not know what they are, right? How do we go about estimating them? Let's see. So, if we get these estimates, what we can do now is to create that equation, if you remember, just like in simple linear regression, and it will come out like this, right? Plus beta 2 x2, right? Plus all the way up to beta p xp. So we are going to estimate them using the same method, least squares. We're going to use least squares, just like we did for simple linear regression. So we choose the beta, we choose beta p, beta naught, all the way to beta p. That minimizes, or that minimize, I mean, it's correct English, right? I think that minimize the residuals, our RSS, if you remember. So our RSS is defined as I equal to 1 and the actual y minus the predicted y squared, like that. And now this is the biggest difference when it comes to multiple linear regression. If you remember, in simple linear regression, our e was defined as yi minus, like this, yi minus, and this was equal to yi, the actual, minus beta naught minus beta 1 x minus beta 1 x, something like this, right? This worked because my e, it was sort of one-dimensional. It was one-dimensional. Where were we measuring? In what dimension were we measuring the difference? We're just measuring the difference in the what? In the y-axis, sort of, because our x was TV sales, and then here TV advertising, and then it was sales. So our difference was in the y direction. How far our point is from the prediction line. That was our e, in the y direction. But in multiple linear regression, the difference is going to be in multiple x's. Imagine our cells depended on TV and radio. So we would have cells is equal to beta naught plus beta 1 TV plus beta 2 radio, right? So here we have sort of an equation that's like z, representing our cells, is equal to, it's a function of x and y, two variables, right? So which means when you're doing your e or your error terms, how far your prediction is from the point itself, or how far the point is from a prediction line, you're going to say how far is it along the x-axis and how far is it along the y-axis, right? Because you now have a situation like this. You now have this being your z, and let's say this is your x and your y-axis. So if you have a line that goes like that, you're going to see how far this point, how far is it on the x-axis and how far is it on the y-axis, right? To this plane. It will be like a plane like that. So it won't be a line. I should say the line, but in this case it will be a plane. It will be a plane like that, right? A 2D plane. So now that's the same thing. In the simple linear regression, we only had one dimension to get the error term. It was just the y direction. But in let's say here where it's dependent on two variables, we'll have our e will be an element of R2, which means our E will have two components. The one saying how far are you from the prediction line, how far is the point from the prediction line in the X direction, and also how far, and the second part will be how far is this point in the Y direction, right? It is very important. I'm emphasizing that because now in our multiple linear model, we have from B1 all the way up to BP, which means the errors we're going to have an error in the one direction, error in, so the error for one part, let's say Y1, this is the actual, and then this is our prediction for Y1. The error here will not just be as simple as this, right? It will be in multiple directions. We are going to say, okay, for Y1, for this part 1, this point up to that prediction, it's not going to be a line, it's going to be something, a plane that has p dimensions, a plane that has p dimensions. We're going to say how far is that point from whatever, I don't know how, if it's a plane or it's sphere, I don't know what it will be, because p dimensions are many, let's just say are many dimensions, right? Whatever, we're going to say from that prediction, how far are you? We're going to say our E is going to be composed of the error in the first direction, the error in the second direction, error in the third direction, error in the fourth direction, all the way up to error in the p direction. Just like here, our p was like with 1 and 2, with 2. So our error was composed of two dimensions, the one in the x and the one in the y direction. That's the same thing here. That's the same thing that I'm saying. So our E becomes a vector like that. When our E becomes a vector, how is our RSS going to look like when we now do this summation? When you now do this summation over all those E's, because this was just an E for Y1 minus Y prediction 1, right? We're going to have another E vector. So this was E error number 1, error number 2 for Y2 minus Y prediction 2, and it's going to be another vector as well for that second point to whatever that the prediction curve or whatever it's going to be. So what that means is now for all the endpoints, we are going to have n vectors composed of these errors that are looking at each dimension, So what's going to come out, we're going to now have what is called a matrix. You can just say a matrix of error terms, right? Let's just say the first column will be the error for point number 1, and it will have the many errors in each dimension, in direction number 1, direction number 2, direction number 3, direction number 4, and all the way up to direction number p. And then E2, the error for point number 2 in each direction, just like here in the x direction and the y direction, and then error number 3. So we have a matrix, and that is different from when we just did simple linear regression. We're not going to get into like the matrix form itself, but the reason why I raised it is because my RSS, if I rewrite my RSS, is going to come out like this: summation of I equal to 1 up to n yi minus beta naught, which is our intercept, that is fine, that is a point, minus beta 1, and it's going to be beta 1 what? xi1 minus beta 2 prediction xi2 minus all the way up to beta p xi squared. Here it's just putting those. So I just means we're going to create a matrix of n terms. So it's going to be up to all the, yeah, I should have written n here and then p as the columns. So the errors will be like this, actually, like the rows, and then the variables will be like p, like that. That's how I should have written it. But yeah, I'm just emphasizing that this is now multi-dimensional. That's what I'm just emphasizing. It's now multi-dimensional, right? So without getting into the mathematics of multi-dimensional, basically you want to choose our beta naught that minimize this. We are not going to get into how to minimize a matrix and stuff like that, but it's the same principle. R will do it for you. It finds beta naughts that minimize that, right? So if we are to apply this to our advertising data, what we're going to find is this let me see, I don't have enough. Okay, let me delete everything so I can just write this table. Cool. So here we're going to find intercept. This is the table that R is going to give us. TV, radio, and then it's going to say newspaper, right? That is going to be our table that R gives us, and it's going to give us the same coefficient. It's going to give us the same values here, the coefficient. So for the intercept, it's going to say this is 2.939, 0.046, 0.189, and then minus 0.001, and then it's going to give us the standard error. The standard error for each of those betas, which is just 0.3119, 0.0014, 0.0086, and 0.0059. And here it's going to give us our t statistic. T statistic is going to be given for the first one 9.42, and then second one is 32.81, third one is 21.89, and then for this one a minus 0.18. And then the p-value, this one is going to be less than 0.001, less than 0.0001, less than 0.0001, and this one is 0.8599. Cool. That is the result from our R when we run the multiple linear regression for our advertising data. Cool. So what this means is, for a given amount of TV and newspaper, let's say so how do you interpret this table? For a given amount of TV and newspaper, when we keep those fixed or constant, it means an increase in 1,000 rand, 1,000 rand increase in radio advertising. What does it lead to? This leads to an increase, a 189 units increase in sales, right? Because the coefficient for radio is 0.189, right? Now let's look at the coefficient for newspaper. It is very, very close to 0. And look at the p-value. The p-value is not significant. We want the p-value to be very small for us to think that coefficient is significant. But this is not small. 0.8599. That is a large p-value. If it's a large p-value, it means maybe newspaper is not what? Is not needed in this model, right? When you compare, what's funny is when you remember, we had two people here that were trying to answer the question. Is any one of these, like TV, radio, newspaper, are all of them responsible for sales, right? Are all of them responsible for sales? The first person would have said, okay, I'm going to run simple linear regression models on each one of them, right? And if you remember from the one for newspaper, the simple linear regression model for newspaper, if you remember, the one that was separate, let me get my notes here. The coefficient for only newspaper, when we ran its own, was 0.055. That was the coefficient with a p-value less than 0.0001. So by itself, you'd have said, yes, it is very significant. But when you put everything together, look at the p-value now. It has changed to 0.8599. So what it means now is the difference between these two p-values when it's by itself, newspaper, and when it's with every other media, the difference stems from the fact that in simple linear regression case, the slope term represents the average effect of 1,000 increase in newspaper advertising, ignoring, very important, ignoring every other factor, every other predictor like TV or radio, right? It was ignoring that because it was a simple linear regression model on newspaper alone. But here it is a multiple linear regression line that is taking into account TV, radio, and newspaper, right? So, in multiple linear regression, the coefficient of newspaper represents the effect of increasing newspaper advertising by 1,000 rand while holding TV and radio fixed. Not ignoring them, but while holding them fixed. They are there. So that is why this one is saying, dude, if you hold TV and radio fixed, and you increase newspaper by 1,000 rand, newspaper advertising by 1,000 rand, what is the increase in sales? The sales are actually going to go down by 1 unit because it's negative. Can you see that? We've increased newspaper advertising by 1,000 rand, but the sales actually go down by 1 unit. That is actually funny. It shows how useless newspaper advertising will be when we already have TV and radio advertising, right? That is very important. That in multiple linear regression, those type of interactions now start to take effect, right? So this actually shows us also that from doing newspaper alone, this is what we would have gotten, right? 1,000 rand increase in advertising budget would have increased our sales of this product by 55 units. That's what we would have seen, right? But then when we put everything together, we see that it decreases by 1 unit. The sales actually decrease by 1 unit. So it means this newspaper advertising, it's actually hiding behind these ones here. It's actually hiding behind TV and radio. And if you want, you can come up with a correlation matrix for these three, and you see that newspaper and radio are actually correlated. And so which means newspaper advertising is just riding on top of radio advertising. It's not very useful, right? You can see that in a correlation matrix, because I think the correlation between radio and newspaper will be something like 0.35 or something like that, right? So that is how we find our coefficients, beta naught to beta p. In our case here, we just have beta naught, beta 1, beta 2, beta 3, right? And then we decide, oh, look at the p-value, which one is useful, which one is not, and stuff like that. But it's the same process as linear model, but just expand, a simple linear model, but expanded just a little bit. In the next video, we are going to look at some important questions that multiple linear regression will be able to answer. Things that we could not answer with a simple linear regression model.